wind is blowing 20 degrees north of west at 15 meters per second, what is the magnitude and direction of the plane's resultant velocity? So this is a lot like the problem that we just did for the warm-up. So let's see, plane's flying west, wind is blowing north of west, so we really just need north and west. We really just need this part of the coordinate plane here. And let's see, the plane is flying west at a speed of 120, and we have the wind blowing 15 meters per second at 20 degrees north of west. So if we draw that, north of west, west is the main direction, but we go 20 degrees to the north of that. So this angle right here is 20 degrees. And this side right here is 120, and this side right here is 15. And to find the resultant vector, we are going to make ourselves a parallelogram. So if you just draw yourself a parallel line here, and a parallel line here, maybe that's about right. The resultant vector, actually let me stop. Question so far. Alright, it might be a good idea for us to go ahead and do the angles here before we draw the resultant vector. So if this is 20 degrees, this angle over here is also 20 degrees. And what would the big angle right here be? So this angle right here. We know all the angles have to add up to 360, or the angles on the consecutive angles in a parallelogram, the angles that are on the same side, they have to equal 180. So 20 and something has to give us 180. So this right here is going to be 160 degrees. And so if we draw in our resultant vector, blue for that, I'm going to start right here. I'm going to go to the opposite corner. And so I like to pick a part of the parallelogram. Typically, if I can, if part of the parallelogram lies on the axis, so like this part right here, I try to use that triangle. It just usually makes things easier if you use the triangle that has the part that's actually touching the x or the y axis. It tends to make the problem a little bit easier. So I also don't like that triangle because it's so skinny and hard to see. So a lot of times I will redraw this triangle, just the triangle, so I can see it a little better, even if it's not really to scale nearly as much. So I can label it a little bit better. So this is 160, this is 120, and this is 15 right here. And so we're going to have to find the magnitude first, so the length of that side. Boone, how would we find the length of that side? Law of cosine. So tell me how I'll set that up. Good. And our x squared equals this. So in the calculator, we should get like 18,007.893 if we square root both sides. We will get 134.193 meters per second. So the airplane is now flying 135.193 meters per second. That is a reasonable answer because it's a little bit faster than 130 and 120. But not so much faster that it wouldn't make sense. Then, whenever we look at this, now that we know this side is 134.193, now we want to set it up where we can find an angle. And the angle we want to find is the angle that actually touches north, south, east, or west. So in our picture here, that's this angle. In our picture up here, that's this angle. I'm going to call it theta. So, Elena, if we want to find that angle right there, what are we going to use? So, how would we set it up? So, we know we want to find sine of theta. Good. Good. Perfect. Very good. Alright, so to solve that, we're going to cross multiply. So we'll get 134.193 sine theta equals 15 sine 160. We'll divide by the 134.193. And so sine theta will equal, and let me show you something also in the calculator here. Change attendance for Richard. I don't think he's here today. If he is, he's not returned. So, for example 9, for example 9, vector A has magnitude 3 feet and direction 20 degrees. Vector B has magnitude 10 feet and direction 200 degrees. Find the magnitude and direction of A plus B. Okay, so this problem is a generic vector problem. It's also going to have something a little bit weird about it. So our first vector has a magnitude of 3 feet, and it has a direction of 20 degrees. So here we've got 20 degrees and a magnitude of 3 feet. Okay. Our second vector is going to have a magnitude of 10 feet in a direction of 200 degrees. So 200 degrees is going to be, right here's 180. It's going to be 20 degrees past that, which is going to put it right here. And 220 are opposite of each other. So this problem becomes weird because we can't really make a triangle with this because those two angles are just in opposite directions. So in this case, it's almost like a tug-of-war game. So if somebody is pulling on the tug-of-war rope with 3 units in this direction, or 3 newtons in this direction, and somebody's pulling 7 in this direction, who's going to win? The 7's going to win because they've got a greater force, right? So, so if you have this, what's going to happen is you're just going to subtract the 2. So if you ever have vectors that are opposite of each other, then you're just going to subtract the 2, 7 minus 3. Oops, I'm already doing the answer, aren't I? Yeah. Okay, let's change this. This is 10, not 7. And so that means over here, we are going to do 10 minus 3. And whenever we do that, we'll get 7. So you're going to have a vector of a magnitude of 7 feet, and it's going to be in whichever direction has the highest magnitude. So a direction of 200 degrees. So if you ever have vectors that are just opposite of each other, you're just going to subtract them. If you ever have, we didn't have any of these, but if you ever have vectors that go in the same direction, you can kind of just like draw them like they're one on the other end. You don't make a triangle, so you just add them together if they're in the same direction. So if you're in a tug-of-war game, if Sadie and Jacqueline are playing tug-of-war, and Jacqueline's losing, and Bethany jumps in and starts to help her and pulls on that end, then you would just add the force of Jacqueline plus the force of Bethany and see if it's greater than the force of Sadie there. So you just add the 2 together if they're in the same direction. Okay, questions? Yeah, so all you do, if they are opposite of each other, so if they're going in, like if you have a plane going north and a wind blowing south, or a boat going upstream and a current going downstream, if they're just opposite each other, you're going to subtract. If they're in the same direction, you add them for that. Unfortunately, they don't give us those very much because they are a lot easier, so I guess they want us to have to work harder for that. Plus, this doesn't happen nearly as much in real life because, for example, if you're in an airplane flying, the wind might be blowing directly against you, or directly behind you, but probably it's a sort of at an angle because the wind blows all crazy directions. You can't guarantee it's just one or the other. Okay, so we now we've done the homework for the problems where the vectors are perpendicular to each other. So I want to we will have a quiz on this either Tuesday or Wednesday. It might be Wednesday next week. That will have vectors. We also have another section we've got to do with vectors. So vector quiz will be Tuesday or Wednesday next week. We're getting ready to do some vector problems that I think are kind of difficult. However, keep in mind the stuff you had for homework last night, where you just got like a vector blowing north and another one blowing west, and you have to tell the resultant vector. You're still going to have some of those problems where the vectors are perpendicular to each other and it's just regular trig. In fact, the quiz is going to have more of those questions than it will these more difficult ones that we're going to look at. Because these can, I think the pictures are really difficult to set up sometimes for these problems that we're getting ready to do. And the other thing is for these problems, I do want you to draw them to scale. So let me just go ahead and I'm going to pass out. We are going to draw these to scale. Because on some of these, they're going to be really hard to figure out if you don't draw them to scale. So let me get my ruler and my protractor. I would suggest using the centimeters instead of inches. Because centimeters are broken up into tenths. So if you need to graph 2.7, you just go 2 and then count 7 little tick marks over. They're a lot easier to use. But you can use either one. It doesn't really matter. Okay. All right. So in this case, a plane is flying in a direction 20 degrees north of west. The wind is blowing 30 miles per hour in the direction 30 degrees east of north. What is the resultant velocity of the plane? So, in this case, we're talking about north of west and east of north, so we really don't need the south direction any. Also, which vector is bigger? The vector that's going to the west, or the vector or the north of west, or the vector that's going east of north? The north of west, right? It's a lot bigger, 430 miles per hour. So when I'm setting up my axis, let's see, vector there, line. When I'm setting up my axis, I want to put the x-axis pretty close down there to the bottom because I don't need the south, really. And then I also know that I know that the vector over here that's on the east side is really small. So I'm going to put because you'll find, depending on how you scale this, it is going to be best to make sure you got it set up correctly. You're also welcome, if you are having trouble drawing it, or if you run out of room, you're welcome to just get a separate sheet of paper and use the whole sheet if you want. In fact, whenever I finally when I was trying to do these well so that I could show results, I just went with a whole sheet of paper for every problem so that I could draw them to scale really well, because it is a little bit difficult to do. So if I'm going to draw these to scale, then I've got a magnitude of 430 miles per hour, and then also a magnitude of 30 miles per hour. So I've got to scale that so that I can fit both of these on this graph. Yours is going to be different than what I've got here because my ruler is different than yours. So I know that, in fact, I wish my ruler was longer here so that it would be closer to what you guys can do. There, I can make it so that it would be better. Okay, so 430 miles per hour. I could say 1 centimeter equals 1 mile per hour, but then that would mean that I've got to, if I do that, then that would mean that I've got to have a paper that's 430 centimeters long, and I don't have that. So even if I did 10 miles per hour for 1 centimeter, that's probably still not good enough, because if I do that, then I still have to have a 43 centimeter long paper, and that ruler that you got there has only got 30 on it, so that's still way too long. So how many miles per hour do you think we should let 1 centimeter equal? So to set, like, if we wanted to know how many would work. So like, we got 430. If we took, let's say if we let this equal 20 miles per hour, then if 1 centimeter equals 20 miles per hour, we would have to divide this by 20 to figure out how many centimeters we would need. So if we do 430 divided by 20, is that going to work? That's still 21.5. That's too big, I think. So let's try something different. What do you guys think? 50? 8.6? I tell you what, what about 30? What does 30 give us? We could fit 14.3 centimeters on our paper, couldn't we, I think? Will it work? So let's do 30. The reason I decided to pick 30 is because, why do you think I decided to pick 30? That way when I divide 30 miles per hour, I'm just going to get 1, right? So this is going to equal 1 centimeter. And if we do 430 divided by 30, we get 14.3 repeating centimeters. So if I'm going to do this, the first vector that we have is in a direction 20 degrees north of west. So north of west, 20 degrees, I would take my protractor, I would put it right here. This is the direction that I should be going. So I would put my protractor right there on the origin, and then from the west up 20 degrees, I would put me a little dot. And then I would take my protractor and my ruler here, and we'll try to get it lined up. 20. It was 20. And it's a lot harder for me to line up my ruler than it is for you guys because you can just move your ruler. And I'm actually going to have to copy and paste this ruler because I need my ruler to be, alright. I need my ruler to be longer here. So I need to draw a vector that has a length of 14.3. Oh, let's flip this one around. Well, I just have to count backwards. Alright, so let's see. 2, 3, 4. About right here. Pretty close. Okay. And let me fix that so it's color and so that. Okay, so then I can label this one. This is 430. Label it with the actual value that was given in the problem. And I can label this angle right here is 20 degrees. Have any trouble getting that one? Okay, and then there we go. Okay. So the next angle is a direction 30 degrees east of north. So north is my main direction here. So I'm going to turn my protractor. Yeah. So we're going to start from this right here, and we're 30 degrees, even though we might still have a problem, because once we do our parallelogram, we might have trouble. But 30 degrees right here, and that's to the east of north. So we're going to line up 0 on north and go 30 degrees to the east of that. And then we'll a vector here that is only 1 centimeter long. I don't like drawing this one to scale because there's such a big difference. But so we've got labeled this side right here 1, and then this angle right here, that's 30 degrees. Okay, so that sets up our two vectors. Questions so far? Alright, now we need to make a parallelogram. So you're just going to take, and you can take your ruler, and you can go from the end of this little vector right here, and just make yourself a line that's parallel to that blue line. And then you're going to start at the arrow here and make a line that's parallel to that red line, which is about like that, I think. Questions? Okay, so I like to do angles before I like to do angles of the parallelogram before I draw the resultant, because I think once I draw the resultant, it confuses me a little bit. So let's start with this angle right here. What is the measure of that angle going to be? The whole thing is not 70, but part of it is 70. Because if this angle right here is 20, then this piece right here would be 70, right? So that whole green angle right there, we would take the 70 from over here, because that makes a 90-degree angle, and we would subtract that 20 to get 70 over here, and we know this part's 30. So this green angle right here, that's 100 degrees. And so if that is 100 degrees, what's the measure of this angle over here? This is going to be 80 degrees. And I like to do that, and you could also, if you wanted, you could go ahead and label this angle right here is 100, this one right here is 80. I like to do that before I do the resultant vector, because once I draw the resultant vector, what color have I not used? Green. Okay. It splits those angles and it confuses me further. Now, I told you earlier, if there is a angle that, if there is an angle that touches the x or the y axis, that's the one you want to use. However, do we have an angle that touches the x or y axis here? We do not. So that means whenever you get your answer, you're going to have to do a little bit extra work. So you could pick either triangle here. I think I will pick this bottom triangle, just because I have labeled my angles there, but there's not really one easier than the other necessarily. So if I pick that triangle, it bothers me greatly. That's what Justice Sheehan would say. He says that a lot in calculus, that things bother him greatly. But if you would, it bothers me greatly that this is such a teeny tiny skinny triangle. Even though it's drawn to scale, which is going to give us a more accurate representation, and on some of these you're going to need it to be drawn to scale. I still have trouble solving this, so I'm going to make myself over somewhere where I've got some space. I'm going to make myself a triangle that looks a little bit fatter, so I can label it a little bit better, and label this 430, and this side right here, oh, I labeled that 1, but I should have labeled it 30, shouldn't I? 30. That is 30. I'm going to label this angle 80 degrees, and then this is the side that I'm looking for. So this is not drawn to scale. And if you don't draw it to scale, what happens is sometimes if you don't draw it to scale, your angle ends up in the wrong quadrant, and you can't figure out where it should actually go. So on these more difficult ones, drawing it to scale is important. But on this one, I would not. So you would find this side. Then you also want to find the angle. You want to find the angle that's closest to the origin. So you want to find this angle here. But that angle is not your final answer on this, which I'm not going to go any further with that right now. I mostly wanted to show you how to set it up. So you would do law of cosines, law of sines, find the missing pieces, and give your answer for this one. So questions? Okay, so what we're going to do for the next 12 minutes here, and what I want you guys to do for homework is I want you to draw a picture for all of these. You do not have to solve them, okay? Just draw the picture for all of these. Please do not solve them, or we won't have anything to do Monday. So don't solve them. Number 1 is done for you. You don't have to do anything else for it as long as you followed along in this. But I do want you to try to draw them to scale. So you can take the rulers and protractors home if you don't have one at home. I mean, I'm sure you've all got protractors laying around your houses that you use all the time. But just in case you don't, you can take these home if you need to. Just please make sure you bring them back because I need them for my classes, of course. So you can take them home if you need to. The rulers, I think, will even click into your binder really well so you don't lose them there. So take them home if you need to, but for right now, go ahead and get started on drawing those. Yes? Can I what? Okay, yes.